The average acceleration of a particle is the rate of change of its velocity during a given time interval delta t. That is, the average acceleration is the change in its velocity divided by the time interval delta t. The instantaneous acceleration of a particle is the limiting value of its average acceleration as the time interval delta t approaches zero. That is, the instantaneous acceleration is the derivative of the velocity with respect to time. Notice that this is the second derivative of the position with respect to time. So let's look at an example. The velocity of a particle is given by the function v of t is equal to 9.4 minus 9.8 times t, where the velocity is in meters per second and t is in seconds. Determine the particle's average acceleration during the time interval from 0 to 1 second and its instantaneous acceleration at the time t equals 1.5 seconds. Okay, so the velocity function is v of t is equal to 9.4 minus 9.8 times t. The velocity at the time t equals 0 is 9.4 meters per second, and the velocity at the time t equals 1 is 9.4 minus 9.8 meters per second, or negative 0.4 meters per second. And so the average acceleration is the change in the velocity, which is the velocity at time t equals 1 minus the velocity at time t equals 0, divided by the time interval of 1 second minus 0 seconds. Which is negative 0.4 meters per second minus 9.4 meters per second divided by 1 second, or negative 9.8 meters per second divided by 1 second, which is negative 9.8 meters per second squared. Now the acceleration, the instantaneous acceleration, is the derivative of the velocity with respect to time. And we can also denote this as v prime of t. And so this is the derivative with respect to time of 9.4 minus 9.8 times t. Using the sum rule or sum difference rule, we have the derivative with respect to t of the constant 9.4 minus the derivative with respect to t of the constant multiple 9.8 times t. The derivative of a constant is 0, and the derivative of the constant multiple 9.8 times t is the constant 9.8 times the derivative with respect to t of the monomial t to the power of 1. And so this is negative 9.8 times the derivative of t, which is 1 times t to the power of 0, or simply 1. And so the acceleration is the constant negative 9.8. And so at the time t equals 1.5 seconds, the acceleration is negative 9.8 meters per second squared, as it is at any given time. So as an exercise, the position of a particle is given by the function x of t is equal to 2 times t squared minus 4 times t, where x is in meters and t is in seconds. First, determine the particle's displacement and average velocity during the time intervals from 0 to 1 second and from 1 to 3 seconds. Second, determine the particle's instantaneous velocity at the times t equals 1 second and t equals 2.5 seconds. Third, determine the particle's average acceleration during the time interval from 1 to 3 seconds. Fourth, determine the particle's instantaneous acceleration at the time t equals 2.5 seconds. And finally, graph the position versus time for this particle. And if you're graphing by hand, only graph the first 3 seconds. Now recall that a particle's displacement is independent of our choice of origin. And so a particle's velocity and acceleration are also independent of our choice of origin. Now for a constant acceleration, the instantaneous acceleration is the same as the average acceleration. And so for any time interval delta t, we have that the constant acceleration is equal to the change in the velocity divided by that time interval delta t. And so the change in velocity is equal to the constant acceleration times the time interval delta t. And this is the final velocity minus the initial velocity is equal to the acceleration times the quantity, the final time minus the initial time. Now we can choose our reference frame so that the initial time is 0, and then the time interval delta t is the elapsed time t since 0, and we have that the velocity at the time t minus the initial velocity is equal to the acceleration times the time t, so that the velocity at any given time t is equal to the initial velocity plus the acceleration times the time. Notice that this is a linear equation in the velocity versus time coordinate system. And so once again we have a linear equation. The velocity is the initial velocity plus the acceleration times the time. Now since the velocity is linear with respect to time, we can choose a final velocity v sub f, and then the average velocity between the times t sub naught and t final is the midpoint on this line segment between the initial velocity and the final velocity. That is the average velocity is equal to the arithmetic average of the final velocity and the initial velocity. So we have that the displacement divided by the time interval delta t is equal to 1/2 the final velocity plus the sum of the final velocity and the initial velocity. And so the displacement is 1/2 the quantity, the final velocity plus the initial velocity times the time interval delta t. This is the final position minus the initial position is equal to 1/2 the sum of the final velocity and the initial velocity times the time interval t final minus t initial. Now once again we can choose our reference frame so that the initial time is 0 seconds, and then the time interval is some elapsed time t since 0, and we have that the position at the time t minus the initial position is equal to 1/2 the quantity, of the velocity at the time t plus the initial velocity times the time t, so that the position at any given time t is the initial position plus 1/2 the sum of the velocity at the time t plus the initial velocity times the time t. Now we can eliminate the velocity at the time t by solving for this quantity in the first equation and replacing it in this equation. Recall that in the first equation we have that the velocity at the time t is equal to the initial velocity plus the constant acceleration times the time. And so the position at any time t is equal to the initial position plus 1/2 the quantity, the initial velocity plus the acceleration times the time plus the initial velocity times the time, which is the initial position plus 1/2 of the quantity 2 times the initial velocity plus the acceleration times the time, all of which is multiplied by the time t. And so this is the initial position plus the initial velocity times the time plus 1/2 the acceleration times the square of time. Now in this equation we can also choose to eliminate the variable t by solving for the variable t in the first equation and replacing it in this equation. So once again, in the first equation we have that the velocity at any given time t is equal to the initial velocity plus the acceleration times the time t. And so the time t is the difference of the velocity at the given time t minus the initial velocity divided by the constant acceleration. Now in the second equation we have that the position at any given time t minus the initial position is equal to 1/2 the sum of the velocity at the time t plus the initial velocity times the time t. We can rewrite this equation as 2 times the displacement is equal to the sum, the velocity at any given time t plus the initial velocity times the time t. And we can now replace the variable t with this expression so that we have the sum, the velocity at the time t plus the initial velocity times the difference, the velocity at the time t minus the initial velocity divided by the acceleration. And so this is 2 times the acceleration times the displacement is equal to the square of the velocity at the time t minus the square of the initial velocity. And so the square of the velocity at the time t is equal to the square of the initial velocity plus 2 times the acceleration times the displacement. So we have a set of 4 equations that are valid for a constant acceleration. Notice that in each of these equations, the quantity on the left-hand side is a function of the time t that has elapsed since the initial time of 0 seconds. Even in equation 4, where we have eliminated the variable t from the right-hand side, the velocity is still an implicit function of time, since the displacement delta x depends on the elapsed time t. Now, if we keep in mind that the quantities on the left-hand side are functions of t, we can simplify the notation of the equations. For example, the second equation is read: the position at a given time t is equal to the initial position plus the initial velocity times that time plus 1/2 the constant acceleration times the square of that time. These equations are called the kinematic equations for the motion of a particle in one dimension under a constant acceleration. So let's revisit our ongoing example and apply some new insight. We have the position function x of t is equal to 1.5 plus 9.4 times t minus 4.9 times t squared. Notice that this is exactly the same form as our second kinematic equation, and so we can simply read off some values. The initial position is the constant 1.5 meters. The initial velocity is the multiple of the variable t, which is 9.4 meters per second. And 1/2 the constant acceleration is the multiple of t squared, which is negative 4.9 meters per second squared, so that the constant acceleration is negative 9.8 meters per second squared. Conversely, if we know the initial position, the initial velocity, and the constant acceleration for a particle, then we can immediately write its position function, and we can exactly predict its position at any given time t. So let's use GeoGebra to analyze the motion of this particle. We will call our position function r, and this is 1.5 plus 9.4 times x minus 4.9 times x squared. Now the velocity function is the derivative of the position function, and the acceleration function is the derivative of the velocity function. Notice that the acceleration is a constant. Now let's hide the position function for a moment and focus on the velocity function. Notice that the velocity function, which is a function of velocity versus time, is a linear function. And let's look at the point where the velocity function crosses the time axis. And recall that this occurs at the time 9.4 divided by 9.8, which we determined by setting the velocity function equal to 0 and solving for the time. So notice that during the time interval from 0 to 0.96 seconds, the velocity is positive since it has a positive value, but is decreasing since it has a negative slope. And that during the time interval from 0.96 seconds forward, the velocity is decreasing and is negative. Now, while the velocity is decreasing, the speed in the negative direction is increasing. So let's return to our position function and hide the velocity function. So for the motion of this particle, we have a beginning location or a beginning position of 1.5 meters. The particle begins moving at the initial velocity of 9.4 meters per second in the positive direction and is slowing down, eventually coming to a stop, and then begins moving in the negative direction with increasing speed. Okay, so we'll end here for today. Next time we will continue our study of kinematics in one dimension. So I hope you have enjoyed the second lecture. Thanks for watching.